electronic issue. How many people online? 2, 3?
3.
Well, the rest will be on notebook. Have you started to record? Really?
Oh, this thing.
Oh, don't think you've done it.
Oh, that's hang on.
That's fine.
Projectable.
What you could do, you get the share content,
Yeah.
share camera, and I think it's, no, not this one. This one, you see? Let me just, this camera. And share camera so we can see proper,
Right.
bigger screen. All right, guys, enjoy your lecture. And you will see me online next week. Teaching on computer. See you guys. Bye.
Right, I think we better have a half an hour seminar, don't you? Because we haven't met for 4 or 5 weeks. Right. Last time we were talking about digital neuron models and digital neural networks, sometimes called weightless, because they don't have the weights of the McCulloch-Pitts model. Remember the McCulloch-Pitts? Inputs, weights, linear hyperplane in the surface dividing space, 2 classes to class recognition. The structure we're looking at is a digital net, which is, pen doesn't write a damn thing. The data comes in the form of numbers. It's a vector, but we can easily represent that as an image, where each pixel is the element of the vector. So a 3 by 3 picture is a 9 element vector. We sample the input, and we're following the ideas of old method, 1959, Browning and Bledsoe. N samples. And the idea of taking N samples is you've got more space to make a decision. If I was sampling 1 pixel and the data was binary, hello there, welcome, we're in seminar mode, so come in and relax. If I was looking at 1 pixel, then if it's black and white, there's only 2 states you can have. So there's only 2 possible decisions you can make on a single pixel. And most problems are more than 2 classes. If, however, I go to 2 pixels, then there's a possibility of 4 states. 0, 0, 1, 1, 1, 1, 0. And there's many ways of separating them. I could have 0, 0 as 1 class, and the other 3 is the other. 0, 0, 0, 1 is 1 class, and 1, 1, 1, 0 is the other class. You can work out the number of ways of separating any group from any other group with a totality of 4 states. If I go to n equals 3, I've got 8 states. And if I go to something reasonably large, n equals 10, there's 1,000 different states. And that gives you much more scope of separating 2 classes. So that's the idea of taking endpoints. We'll have the n-tuple size is the sampling size, and they will sample the input space. So a simple linear mapping, n equals 3. I would have a structure like that. Taking the functions, f1, f2, and f3, to get an overall response, we sum them, and we take a threshold, and we get an output. Right, the implementation of those functions, memories, PROM technology. You don't wire up discrete case. And to sample a 3 input space, so let's put some numbers on here. N is the number of pixels, little n is the sample size. These are the logic functions. And we sum threshold. Now, I showed in the last lecture, I think, the behavior of the system can be changed quite dramatically by the way we sample the input. This is a regular row-by-row sampling, and it's easy to follow what's going on. And I gave the example of the vertical bars, do you remember? Where I trained on 8 vertical bars, and with a particular sampling here, changing these connections, if it were row by row, the system would recognize everything, and therefore no discrimination, no good. If I have, however, changed for that particular problem from horizontal samples to vertical samples, because they match the features I was looking for, vertical bars, I found the system would only recognize the training set. So we have 2 extremes. And in real systems, the number of ways of wiring up a system here is potentially infinite. If I take a 512 by 512 sample, the number of ways of selecting the pixels is, I think, 512 factorial, which is an infinite number. Now, you've got that flexibility with this system. You don't have that flexibility with the McCulloch-Pitts neuron. The mapping is a single mapping, it's a total mapping, and there's only one choice of mapping, the vector for the input. So this gives us more flexibility. Right. Now let's take that idea. The new work today is going to be looking at the threshold, which will change the generalization. Let's not go there at the moment. Let's take an example, an exam question example. Let me take a pattern recognition case, and I want to recognize a character. I used T before. Let's change another character. Let's take X. Now on a 3 by 3, that's a good representation of the character X. Okay. Now to generate a training set that's representative, a typical trick in exam questions is to say, let's add noise. And if you see if I say add 11% noise, what do you think that means on a 9-pixel image? Or approximately 11% noise. Well, I used to say 11% noise, and it used to baffle students in exams, and I had to discreetly go and give them clues, and I got into trouble. So nowadays, I would say 11% noise, which is equivalent to changing 1 pixel every time you grab that image. Because 9 pixels, that's approximately 11% of the image. So that is change 1 pixel in training. Right. So let's train that network on that data, and let's call the input ABC. And let's now have a look at F1. Right, the columns are labeled ABC. We could have the noise on the first pixel, the top left-hand pixel. What would be the term in logic F1 that would respond to that interval with the top left-hand pixel change? It's now cross-assume is 1, assume it's 0. It's 0, 0, 1. What is the function going to be? Input is 0, 0, 1. I want an output. Come on, level 1. F is 1 when A is here's the data going in. Top line is going to be 0, 0, 1. A, B, C. There is that sample with the noise changing that 1 to a 0. What's the logic function? Come on, you have me on, aren't you?
Not A, not B, C.
Thank God for that. Not A and not B and C. Right. If the noise is in the middle pixel, what is the interval in the top row? Yeah, and so it is F equals
ABC.
ABC. It was not A and not B and C. The function now becomes not A and not B and C, or ABC. And immediately that trivial but brilliant property, you haven't lost the response to the first pattern, because the logic function still responds to 0, not 1. So the function now becomes not A, not B, and not C, or A, B, C. And if the noise is in the top right, what is the logic function?
A, B, not C. Or A, not B, not C.
A and not B and not C. Or if the noise isn't in the top row, it could be in the middle row or the bottom row. Remember, each grabbing of that frame, 1 pixel is changed. That's the effectively noise. If the pixel is elsewhere, what is the last term going to be?
A, not B, C.
A and not B and C. So that is the logic function for F1, which will recognize the top row, the top interval of the training pattern with 1 pixel noise added. Okay, now work out F2 and F3 for me, please. I'll give you a couple of minutes. Okay, the first 3 rows do F2, the back 2 rows do F3.
Sir?
Yep.
If you increase the percentage of the noise, does this mean you have to change more than 1 bit? Or
This question guarantees 1% noise, 1 pixel noise.
okay.
And yes, it's an artificial problem because noise could vary. If you change the noise, yes, there will be more data going in. In this case, only 1 pixel in the 9 pixel in interchanges. Any suggestions? Anybody totally lost? It's just that you've forgotten all your logic from level 1 and level 2. Must be Dr. Deere dulled your brains in level 2 because level 1 was exciting. Can't even remember, can you? Yep, any suggestions?
F2.
F2, yes?
A, B, not C,
A and B and not C, or
not A, B, C,
not A and B and C, or
not A and not B and not C,
not A and not B and not C, or
not A and B and not C,
not A and not B
B,
and B
yeah.
and not C. Okay? F3, back rows.
Not A, not B, C.
Not A, not B, C,
Not
or
A, B, C.
not A and B and C, or
A, not B, C.
A and not B and C, or
What's the point?
There's A, B, C.
A B, C. That's about right. Okay, we've got three functions. Now, of course, in implementing that in the original structure, there, we wouldn't have these discrete functions. We're using memories. So if I now put those functions in a memory, here's the input. Three input functions, of course, need 8-bit memories. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And these are the inputs. Here's the output F, 1, F2, and F3.
Sorry, Professor.
And the addresses, of course, are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. That's the same for all of them. Yes?
I think the second term for F3 is wrong.
Right, let's go back over. Who gave me the wrong answer? Right. Go back to the image that's going in. We'll look at the bottom row. If the noise isn't in the bottom row, it is A and not B and C. F3 we're looking at, are we?
Yeah.
A and not B and C. Yes, we've got that one. That's correct. If the noise is there, that becomes a naught. It becomes not A and not B and C.
Should it be the same as before?
Which is that one. It should be the same as the first, actually, shouldn't it?
Yeah.
Right, let's carry on checking. If the noise is there, it's going to be A, B, C. And if the noise is there, it's going to be A and not B and not C.
That one is not there.
So that one is wrong. That's not A, that's naught, 1, 1. Naught, well, that cannot happen because there's 2 bits of noise there. So that one should be
Yeah, not B, not C.
A and not B and C. Not C. And that should be the same as the first one. Yes, yes, yes. A and not B and C. No, it's still not the same, is it?
Yeah, it is there on the top.
A and not B. Now that let's check again. A, not B, C. We haven't got the one with the noise not in the bottom row.
We do. It's the first one.
Oh, sorry, I've got misreading that. My handwriting's so bad. Yes, so we've got that. Noise there will be A, B, C. Got that. Noise there would be A, not B, not C, which is that one. A noise not in the bottom row would be A, not B, C. Yeah. Okay. Right, now put those functions in the memories. Make sure you can still implement a logic function in a memory. So
So there are only 3 terms for the last function, right?
it should be 4.
But there are
1, 2, 3, 4.
2 are the same, the first and the third.
Right, let's go once more. Let's get this right. No noise in the bottom row will be A and not B and C. A and not B and C. Let's change the color. We have got that. A and not B and C. Noise there will be not A and not B and C. Not A and not B, C. Is that one? No.
No, it should have been the first.
The first one.
It should be. I was right.
It was before.
Right, so that's that one. Noise in the middle is going to be ABC, which is that one, and noise there is going to be A and not B and not C, which is that one. So that is correct, yes? It should be the same as the first function, because the intervals are the same initially without noise. So this should be the same as this one.
In the first function and the third one, it should be A, not B, not C.
A and not B and not C. So does it mean I made a mistake?
Just in writing, but you said it right.
Oh, yeah, okay, right. Okay, are we there? Plug it into the memories, just to make sure you can do that. What's the contents of the first memory? Here it is. The values of the intervals with the noise or without the noise will be the addresses. The addresses are labeled above the memory. The contents of the memory is initially 0. When the term of the function has been identified, that location becomes 1. So for the first function, not A, not B, C is location 1. Yes? It's a 1. A, B, C is 7. It's that location. A, not B, not C is 4, it's that location. And A, not B, C is 5, it's that location. All the others are zeros. Correct? And of course, we're smart people. We know F3 is the same as F1, so don't bother about F3. We can put the same contents in F3, which is going to be 0, 1, 0, 0, 1, 1, 0, 1. There's only F2, the function, to implement. And the terms for F2, it is going to be 1, 1, 0, which will be 6. 6 is that column. 3 is that column. 7 is that column. And oh, I've got the wrong one, damn it.
That was 0. The 7 was 0.
I'm doing F2, aren't I?
Not A, not B, not C.
Which is 6, 3, 0 is, and 4. So that's a 0 there. And so that is, the last one was 6, 3. So it is 6, 3, yes, 0, and that is 2. So check those are right. Those are the 3 logic functions that have come from the training set. You're now in a position, having got those functions, to test the patterns. So let's put in a pattern. Well, first of all, the original pattern. It hasn't seen the original pattern because after the original pattern has been captured, 1 pixel of noise has been applied. So this is a new pattern. What is the response to that pattern? Let's put the outputs are. You can have a response of 0, 1, 2, or 3. Depending on the number of ones coming out of those 3 functions. 0 is where they're all outputting 0. 1 is where one of them is 1. 2 is where 2 of them is 1. And 3, of course, is where they're all 1s. Okay, what's the sample of the first interval? Top line in decimal.
2.
2. Hang on, we're getting confused. X is 1 and dot is 0. 5. I haven't made. Have I mixed that up all? Damn it. Let's just check. F1. The states of F1 are all the states of F1 is going to be A, not B, C, yes, that's correct. A, B, C, yes. Not A, not B, C, yes. Yeah, they're right, they're right. Panic over. So, where is it? We've got 5 going into the top function. Location 5 is a 1. F1 is 1. 2 is going into the second function. Location 2, 0, 1, 2 is 1. 2 ones. And 5, same as 4, R is 3. It's recognizing it. Okay, test it on another pattern. Does that look like an X or XE? And it's 3 by 3 low resolution. Would you expect that to be an X or not? Okay, what is it? What's the score?
3.
3? Everybody got that? Anybody completely baffled?
Yeah.
Right. What's the state on the top interval? 1, 1, 1.
Yeah.
Black is 1, cross is 1. Address 1, 1, 1 to that memory. Addresses that location. What's in it?
1.
A 1 comes out. Middle, 0 at 1, 0. Location 2, middle function. Location 2, a 1 comes out. And 3 is the same as 1. I think that's response is 3 out of 3. Okay, let's get one that doesn't work. Let's take a letter L. There's your functions. What's the score for the L letter? Top state?
1.
Okay, top state is 4, location 4 is 1, F1 is 1, yes. Middle row?
0.
0. Bottom row?
1.
2 out of 3. Not giving a maximum score. And let's put in a silly pattern. What's the score of that one? Must be out of 3.
1 out of 3.
1 out of 3. Okay, less likely than 6. And working backwards, because we know the functions, can you devise a pattern that will give a score of 0 out of 3? Top row 0, 1, 0. Middle row
0, 0, 0, 0.
0, 0, 0.
And then 0, 1, 0.
0, 1, 0. So that pattern is nothing like an X according to this system that's learnt X's, little noisy X's. Everybody understand why that's 0? What we've had to do.
No.
So
No.
that would be give 1 out of 3.
1 out of 3. You got it wrong, have you?
It is 0, 0, 1 in the
You put
second
0,
row.
0, 1.
0, 0, 1.
That's not it.
Okay. So everybody understand why that's giving 0? the top sample, top row is address 2, and address 2, and the top function will output a naught. 001 will address location 1, that's a naught, and 010, which is 2, will give me another 0 pattern. Naught, naught, 1,
Not.
naught, naught, naught. Oops, 1. Okay, so you're getting the hang of this. So what we've done, we've taken a single pattern, we've put noise on it, and we're able to generate a set of patterns which will give a score of 3 out of 3. Then other patterns only give 2 out of 3, 1 out of 3, and finally the patterns that give 0 out of 3. Okay, so let's sort of now move to new material. Let's have a look at the number of patterns that the system recognizes. So this really is the generalization. Right, generalization, I'm going to use the output threshold. Now, the output threshold in the analog net, it simply moves the hyperplane. It doesn't change the amount of generalizations. It just gives you different generalizations. Now, in the case of generalization with the analog net, we can have a profound effect on the number of patterns the system recognizes. It's a useful control on the net. So there's 3 types of generalization I want to look at. And the first one is AND generalization. And the AND generalization is where, in the case of a simple example, the response is 3 out of 3 for a 3x3 image. Why is it called AND generalization? It's because if I took this original structure, there it is, there's the original structure. If I'm setting the threshold t equals 3, it is equivalent of replacing the summer and the threshold with a single AND gate. In other words, I'm looking for a response of 1 on each of the inputs before the output is 1. It's exactly the same as, say, setting a threshold. So that's where the term AND generalization comes from. So, G AND can be calculated by this formula. It is the product series, pi, I equals 1 to n over little n, which is the number of functions. So in this case, 3x3 image, n, the total number of pixels is 9. The incremental size is 3. We're going to have our 3 functions. So those are the 3 functions. And the contents of the product series is ki, where ki is number of bits set to 1 after training in the ith function. So, going back to my train system, there were my train functions. This is the first function. and ki are the number of bits set, and if we count them, 1, 2, 3, 4. So for this particular example, K1 equals 4. Go back to the second function, we do the other two at the same time. For K2, 1, 2, 3, 4, and K3, F3 is the same as F1, so K3 is also going to be 4. So all the numbers of bits set in each of the functions in this example are 4. And that, of course, is exactly the same as saying how many entiples have occurred at that sampling point in the training. It's just a range of different entiples at each sampling point. So, if each of those Ks are 4 for this particular problem, for that cross with 1 bit of noise, trained with an output threshold of 3, how many patterns will it recognize? It's a product series, so it is K1 times K2 times K3, and that is going to be 4 4s are 16, 64. So, having trained that net, 64 patterns will be recognized. 9 of them will be the training patterns. So the generalization is capturing 55 new patterns, which are, according to this net, X-like. The question is, have a look at those 64, look at 64, 50, 55, and perceptually say, are they T-like? Are they X-like? Do they actually perceive the X shape? Are they recognize an X shape, which is not the same as the training pattern? So if it's recognizing 64 patterns, remember I gave you a set diagram, I think, last time of the behavior of these. So if we have the set diagram, there is your universe. And for my 3 by 3 binary pattern, what's the universe size? Pattern universe. How many patterns can I display on a 3 by 3 binary array? 8. Any more suggestions? Okay, you don't know.
9 factorial.
9 factorial, not quite. That's better. You can't work it out, or can't remember, or go back to first principles. 1 pixel. How many patterns? 2. Good. 2 pixels. 4. 3 pixels. No! 8. 4 pixels.
2 to the size of
9 n pixels. N pixels, the general formula. 2 to the n. N is 9. What's the universe size? 2 to the 9 in English? We don't remember these powers. 512. It's big, isn't it? Just for a 3 by 3. Deceivingly big. If I go to 4 by 4, though, there's 20. 4 by 4, what's the universe size? 2 to the 16, which I think is
4,000.
60. Is it 2 to the 16? 2 to the 10 is at 1K. And it's 65,536. Unbelievable. Just think of that for a moment. When we deal with real data, people just don't realize how big the problem is. If we go to 4x4, 16 pixels, there are 65,536 different pictures that you could put in. And of course, my favorite number comes up again. If I go to 16 by 16 bits resolution, what is the pattern universe? Big, yes.
Power 16 by 16.
But 16 by 16 is 256. 2 to the power 256. I don't understand 2 to the power, I can't imagine them. Let's assume 2 to the 3 is 10. I know it isn't, let's approximate that. So if 2 to the 256, divide the power by 3, and I get a power of 10. 2 to the 256 divided by 3, roughly 80, just approximations. So I've got a pattern space on a 16 by 16 array of 10 to the 80. How big is that?
Infinity.
It's damn near infinity, because if you talk to Akram Khan or Paul Kybird, he'll tell you that's the number of fundamental particles in the universe. And what's interesting, of course, this is the size of pattern space. And then poor old Elon Musk comes along and says, don't worry about my collision software. I've trained it on 250,000 examples. And everybody says, 250,000? That's a huge number. It's a raindrop in the ocean of the total number of patterns that could occur. And when you're dealing with systems, okay, a lot of those patterns are just noise. But if a piece of electronics goes wrong, it's been flooded with particles and the CCD sensors short out, you can get random noise patterns. And you'll be driving along one day and something will come along which you shouldn't hit, and the system doesn't recognize it, or it recognizes something that you should hit, and unprovable systems, so beware. 250,000 in real-time patterns is tiny. Anyway, I'm diverging a little bit. Right, we're getting back to the set diagram. This particular problem, 512 patterns in there. The training set I used for my X with noise will be a set in there. And this is the training set. Let's call that TX. How big was TX, the training set? So the X's I was using with noise, how many patterns did I use? There's the pattern with noise. How many patterns are there with 1 pixel difference from that one? 9! So the training set is 9. This network has generalized, and we discover that it would recognize a generalization set. Let's call that GX. That is GX. And GX, we've worked it out, was how many? How many patterns on that train network? 64. So that is 64. What, of course, is unknown in this problem, in almost all problems, is how many patterns are perceptually the same as X, interpreted by humans. And so that is the data set of all possible X's, which we don't have access to. And supposing the data set for all the X's, let's call that dx, and its size is unknown. But ideally, what we want to do if this learning system is going to do useful work, we ideally want gx to be equal to dx. And in practice, we can never get that. It is safe if gx is larger than dx, as long as it doesn't overlap any data set from another class, because I'm showing only one class in this universe. Of course, there are as many classes as objects you can recognize. So all the other classes fit in there. So if that were the case, we've got a generalization set of Gx equals 64. If it's not matching the total data set for that particular class, we want more generalization. Now, to get that in a digital net, if I go back to the original diagram, forget about the AND gate, which is equivalent to a threshold of 3. If I change this threshold here, more patterns are going to give a response. If I only require a score of 2 out of 3, I'm going to get more patterns. If I only require a score of 1 out of 3, a lot more patterns. So by changing that threshold, I can effectively change this red set here, making it bigger or smaller. So we know what and is the tightest generalization. It's requiring all the outputs to be 1. If I go to the other extreme, we have OR generalization. Now go back to my original system diagram. T equals 3 is equivalent to AND gate. If I set the threshold at the lowest non-zero value, which is 1, that would be equivalent of this summer and this threshold acting as a logical OR gate. It gives a response if one or more of the inputs are 1. It only doesn't give a response when all the inputs are 0. And that will give you much broader generalization. Now, with OR generalization, the equation GOR is equal to the product series of what? Well, we've got a problem. Because with AND generalization, there is only one condition of the outputs of the logic functions which will exceed the threshold t equals 3, all inputs being 1. Only one situation. If I replace that with a lower threshold, with the equivalent of OR generalization, I can get a response if one of the functions is 1, or 2 of the functions is 1, or 3 of the functions, any combinations. And that can add up to a lot of different calculations and instances where the OR generalization is working. So let's put our finger caps on. That's not the way to go and calculate OR generalization. What is the unique input condition for OR generalization?
As long as 1 is 1, the output is 1.
Yes, but I've got to then check all the possibilities go through the net. There is, instead of thinking about the patterns that give an output of 1, what if the patterns are given an output of, the inputs are given, functions are given an output of 0?
Yeah,
That's unique. So don't calculate the Gn by the product series. Calculate not GOR. And not GOR is the patterns not in the generalization. So not GOR will be a product series, I equals 1 to n over little n. Now we want, go back to my original train function. There was my train function. I want F1 to output a 0. How many ways of outputting a 0 are there on this? 1, 2, 3, 4. So if I want F1 to be 0, there are 4 possibilities. It turns out it's symmetrical. There's 4 there as well, and there's 4 there. So if I want to calculate the probability of all the functions outputting a 0, it is going to be general. 2 to the n, total number of states for an n input. In the case of n equals 3, 8 states, 8 locations in the memory, minus the number of bits set to 1, which will be the ki we used in the AND function.
Without the equal sign, right?
What was that?
Without the equal sign between the pi and
Product series. So it's a symmetrical problem because 4 bits are set and 4 bits are not set. So you should be able to deduce that the patterns not in the OR generalization set in this particular example are k1 times 2 to the n minus k1 times 2 to the n minus k2 times 2 to the n minus k3. It's again going to be 4 by 4 by 4. Which again is equal to 64. You with me? Sort of. 2 to the power n. N is the sample size. 2 to the power n is the number of inputs, or the number of locations in my memory. 1, 2, 3, 4, 5, 6, 7, 8. 8 locations, 3 inputs, 2 to the 3. For this particular case, n is 3. If n is equals 4, it's going to be a bigger function. Right. If I've calculated not GOR, I can now go back to my GOR. And GOR, general case, can somebody suggest a formula for GOR? If I've got not GOR?
not.
No. No, it's not binary. It's not binary. I've got the total number of patterns. I've calculated the ones not in the generalization set. It's going to be not 1, but
1 minus.
U, the universe, minus. So GOR is going to be equal to U minus not GOR. And remind me, for a 9-pixel image, what was U? 512. So GOR in this case is going to be 512 minus 64, and that is going to be 448, somebody says. Huge generalization. In fact, that's half the universe in this particular case. So it looks as if that is going to be excessive generalization. Just go back to the original function. There is the train functions. Give me a pattern with GOR output generalization, a threshold, couldn't a threshold of 1. Give me a pattern that will give a response and be classified as an, of course, with GOR, or generalization.
All ones.
All ones. Do we need to draw it? All ones. 1. Yep, just straight away, first top line, we've got a 1. So it doesn't matter what the other 2 are, we're bound to exceed the threshold of 1. Give me another pattern.
All of them.
There's a hell of a lot of them. For almost any random pattern, you've got 80% chance of getting the right one. Give me another one. Now, give me a pattern that is not in the generalization set.
There is no.
No, one. No. You got it, yeah. So, if I go back to my set diagram, if that was G and, the data set, the green set remains the same because that's the real world. If I have G or, the green set is going to be much bigger. In fact, it's going to occupy pretty well the whole of the universe. So that is too much generalization. So we've got a situation, even with this simple example, that G and is too constrained, G or is excessive. So what's the middle line? G and is a threshold of 3. G or is a threshold of 1. What else is there to look at? Threshold of 2. 3, 1, 2. So the third type of generalization is in this case, it's t equals 2. And I think we've come up to 10 o'clock. Shall we take a 10-minute rest break?
Yes.
And I'll resume at 10 past 10.
Sir, can I get pictures of the
What do you want? That?
the first meeting?
That?
Yes. And those? The other ones? Is there another one?
I think that's about all the. Oh, that one possibly.
Thank you.
Because they were going every day for 4 months, 7 days.
No.
When they didn't.
This is good over here.
Yeah.
It's the first time this is very it's the first time I'm doing this. No.
Right, guys, you're fit for another half an hour, 40, 50 minutes. Right. You can set the constraint on the logical network that every function has to respond before the pattern is specified. That is equivalent in our simple example of having a threshold of 3. On a much larger resolution system, it would be a threshold of capital N, the number of pixels, divided by little n, the sample size, which would be the total number of functions for a complete mapping input. The other extreme was having one function firing to give you classification. In practice, that is hugely overgeneralizing. We've seen with our simple example that will swallow up about a half of the universe. And because our example is so simple, we've only got a threshold of 3, 1, and 2 in the middle, where the threshold is not the maximum, but it's a variable. And that's what I want to look at now. So in our simple case, and in practice, one always uses a threshold, not a and or generalization. They are too extreme. One doesn't generalize enough, the other overgeneralizes. So although we're doing a calculation to see how it behaves, this would be a variable of the system parameter you can calibrate during evaluating the system. So threshold of 2, what is happening? If I go back to the original diagram, the trained network, there it is. We found a unique condition for the AND function. It's when all the functions are outputting a 1. We found a unique condition for the OR, which in fact is not OR, where none of the functions are outputting. But with a threshold in between, there is no unique condition for either being in the generalization set or out of it. So you've got to work out exhaustively all combinations of getting a threshold and a response of 2 or more. So if I look at this train structure, clearly, if this is 0, if I'm accessing locations with a 0, and this is 1 and this is 1, it's a response of 2. If this is 0, this is 1 and this is 1, 2 out of 3, and 1, 1, 0. So there are 3 conditions in this simple example where we would get the score of 2 out of 3. Any others?
We're going to keep it 2.
Threshold of 2, we can get 0, 1, 1, 1, 0, 1, 1, 1, 0. And there's a clue. What is also above a threshold of 2?
3.
3!
1, 1, 1.
And 3 is what? It's the AND generalization. So with this method, you can work out the scores for the individual 2 out of 3, but you've also got to add the AND generalization set, because that will also be above the threshold. And there's only one way of doing it, is to slog through all combinations. So G T equals 2 is going to be the individual product series of getting 011, which will be 2 to the n minus k1. That's the probability of getting a naught here, where k1 is the number of bits set in the first function, multiplied by, again, a product series. It is going to be k2, and that would be the number of ways of getting a 1 from the second function, multiplied by k3. And that will uniquely tell you the number of patterns that gives a 011. We've also got to add to those the possibility of getting a 101, which will be k1, probability of getting a 1, the k1 from the first function, times 2 to the n minus k2, probability of getting 0 in the middle, times k3, plus k1 times k2 times 2 to the n, 2 to the n minus k3, plus G and. Don't forget that. These pens are running out. So, notes. Now, it's not, for this example, not as bad as it seems, because it just so happens it's symmetrical. We've got the same number of noughts and ones here. So the first term is going to be, this one here is going to be 4 times 4 times 4. You with me? 4 times 4 times 4. We're lucky. It's going to be easy to work out. 4 times 4 times 4. Because the k's and the 2 to the n minus k is always 4. So in this case, it's going to be that times 3. Plus G and. So let's work that out. 4 times 4 times 4 is 64. 3 64s, 180. And G and was 64. It's 464, 256. I think it's 256, check it. Yep. So there we've got a situation, the same training data, by changing the threshold, we have a generalization set of 64, reduce the threshold slightly, it can go up to 256, and if we put an OR threshold, it was 487. So that is a very nice control, which doesn't involve any training, it will change the generalization properties. So, in practice, one wouldn't do these calculations because large systems are, well, there's a huge amount of combinations of getting an m out of n response or n inputs. But it's a variable, it's a system parameter which you can use to calibrate a system. Right, so that is generalization. Calculating generalization. Right, next thing. The amount of training of the system. How does that change its behavior? Well, in any problem, of course, training is what you make it, as long as many patterns you choose and the quality of the patterns. So there's no formulaic analysis of the effects of training on performance, but we can get some empirical results, some general trends as to how training affects the performance. And what I want to plot out is a typical graph of performance, that's percentage correct, against training numbers. And the number of training patterns, and also I'm going to use varying n sizes. So if I have, say, n equals 2, I might get a performance that looks like this. It will rise as the number of training patterns increases. It will level off. If the system is noise-free, it should remain at the maximum level, but in practice, no systems are noise-free. Noise will add unwanted data to the training, and it may start to overgeneralize, and it will fall off. So we get a performance like that, and that could say n equals 2. If I use a larger interval size, initially the performance may be less good, but with more training, it will go to a higher value. And that would be n3. Why is that happening? Well, we've got a larger interval size. There's more possibility, more space in that. We need more patterns to get the whole range of patterns. So in the early stages, the n equals 2 might be better, but as you carry on training it, it discriminates more because it's got more resolution at the interval size. And we'll get a series of curves that look like this. And what we find is that the performance, if we're aiming for 100% there, it sort of asymptotically goes up to 100%, but never quite makes. Now, the actual shape of these curves, they can be very peaky if it's a well-defined group, or they can be very spread out if it's a noisy set of patterns. In general, the rule to take from that is better performance but you need more training. So, if we're now thinking of hardware, building these systems, let's have a look at the cost. And I'll go back to my original diagram. That simple example, we had n pixels on the input, capital N pixels. We had a little n sample size. 9 sample size 3 functions. So the total number of functions will be the resolution divided by the sample size. The second thing is the cost of building the functions in terms of memory. Go back to this diagram. 3 inputs, implementing it in a memory, I need 8 bits of memory. In general, n inputs, I need 2 to the n bits of memory. So the cost factor we can generate from this cost in bits is going to be the number of functions times the number of bits per function. So if I'm now taking that, let's have a cost equation. C is going to be equal to the number of functions will be n over little n times 2 to the n, which looks pretty harmless, and that's going to be number of bits. And n is the resolution, and little n is the interval size. So, in our system, n equals 9 and little n equals 3. The cost is going to be 3 times 2 to the 3, which is 2 to the 8 is 24 bits. And of course, there they are. There's your 24 bits. And remember, yet again, a misunderstanding that's quite widespread in mechanical engineers. We are not storing patterns. We are not storing inputs. We are storing the response to those inputs. I start off with that network. It is 24 bits. I train it on one pattern, it's still 24 bits. I train it on 1,000,000 patterns, it's still 24 bits. That memory size doesn't change. And these systems are not storing patterns, they are storing the response to patterns. And we think that's what goes on in the brain. Because you don't have a filing cabinet memory in your brain where information is slotted in. You have functions that respond to stimuli. And clearly, we can think of many things with a fixed amount of hardware. And that's exactly what the system is doing. So,
sorry, can you go back to the first page of amount of training?
The
First page of amount of training.
that one?
Yep.
Little n, performance there, total performance is lousy. Increase n, this is a general curve, needs more training, but the maximum response will be higher, but more training patterns. As we keep increasing n, it gets better performance, but more and more training is required. And if you undertrain a high resolution system, it doesn't perform well. It's a little bit like the problem we have with the analog net. If you only train it on a few patterns, it works. Because it hasn't seen the range of information that can occur from only a few samples of patterns. So now we come to the cost. That little system was 24 bits. Let's now take a high resolution system. Let's take a 16 by 16 by 1 bit. So that n there is going to be 256, and let's take a sample size of little n equals 4. The cost of such a system, total number of functions is going to be C equals 256 over 4 times the cost per function is 2 to the 4, which is 64 by 16. I think it's 1 kbit. Yep. Okay, so that's the sort of cost that you might need for character recognition. Not particularly expensive, quite nice little things. But 16 by 16, even though that is an almost infinite input space, if you had 16 by 16 on your phones, you would be most unhappy. You wouldn't regard that as a good quality image. In fact, it would be bloody awful. It would be worse than the pixelated images you try and smooth out by image processing on your eye when you want to see what's hidden behind them. Face recognition, higher resolution. 512 by 512, minimum. Let's take an interval size n equals 8. Cost there. Cost is going to be, number of functions are going to be 512 by 512. Let's have that as a power of 2. It's easy to handle. That's going to be 2 to the 18 divided by 2 to the 3 equals times the cost per memory, and that is going to be 2 to the 8. If I sort that out, 2 to the 18, 2 to the 26, 2 to the 23. And 2 to the 23 is, well, 2 to the 20 is 1 meg. It's going to be 8 megs. Or MB. Getting bigger. If you want to do wide-scale, high-resolution surveillance, recognizing road conditions or whatever, what's your phone resolution these days? 4,000 by 4,000? 16 megapixels. Okay. So go 4,000 by 4,000. And let's take an interval size of 20. Right, that's looking quite hefty in terms of hardware. The cost there is going to be, well, let's have this a power of 2, 2 to the 12 by 2 to the 12, 2 to the 24, divided by, oh, I'll have that 16 is easy, divided by 2 to the 4 times the cost per memory is 2 to the 16. 2 to the 16, 2 to the 40 divided by 2 to the 4 is 2 to the 36. And 2 to the 36 is 8 gigabits. Getting quite big. But by today's technology, still not unreasonable. So that's the sort of memory we might need for practical systems. Right, I've got 20 minutes. Let's start on a hardware system. Right, third year project. We've all got your projects, but if you're going back 3 months, I might give you a project. Build one of these nets. Get it up and running. Go back to the original concept. This is now going to be, instead of 9 pixels, it's going to be, let's take the intermediate one, 512 squared. It's going to be 2 to the 18 pixels. The memory size, I think I quoted in that cost one, was n equals 4. The number of connections, if I'm connecting the pixels to the processor, 9 connections in that one is manageable. 250,000 wiring connections in practice. Pictures come from a camera. Camera access time, or standard TV, is about 100 frames a second now. Pretty slow. We talk about milliseconds to capture a picture. If I'm using memories to implement logic functions, what's the access time of a memory these days? Come on. Nanoseconds. 5 times 10 to the minus 9. That's a fast one. Let's even go to a microsecond. 10 to the minus 6 access time. So, if you were building this system and you did it as this schematic suggests, a parallel system, you would find this would take milliseconds to update because it's coming from a camera. And when you've got the information in that image stored in the frame store, accessing these memories would take microseconds. So there is a completely imbalanced duty cycle. The data is being collected slowly, and as soon as the data is there, the response is almost instantaneous. And these functions were there doing nothing for 999,999 microseconds, and the 1 microsecond when the data is there, it will give us response. So we don't need a parallel system. So, and also the problem, the memories we're using for these functions are relatively small. If I was choosing n equals 4, 16-bit memories, you can't buy a 16-bit memory. They are so trivially simple. Yes, you go back to 1950, yes, it was state of the art. But they don't exist now. You're talking of gigabit memories and costing very little. So we've got to utilize large memories to implement small memories. And that can be done. Again, we're going to go back to some of the level 1 logic design material. So, hardware implementation. Let's take it for a system which is n equals 512 by 512 and little n equals 4. Right, total number of functions is going to be, that's going to be 2 to the 18. And this is going to be 2 squared. So the number of functions is equal to 2 to the 16, which is 60, I'll get this wrong, 4, 16, 32, 64, 128. Right. The total amount of memory I need which is the cost function, is going to be 2 to the 16 times n equals 4, 2 to the 4, which is 2 to the 20, which is 1 megabit. You can go and buy it for a few dollars.
Shouldn't you divide by something?
2 to the 18, 16, yeah, 1 megabit. So we take 1 megabit memory. It's a bit organized memory at this stage. Byte organized is interesting. We get parallel networks side by side, but let's go for the single bit organized memory to start off. 1 output. How many address lines? 1 megabit memory, 4 address lines. How many addresses can you get on 4 bits? 16 addresses, and you want 1 million addresses. I think you're a little bit short on the number of address lines. Okay, back to first principles. If I have 4 bits, go to the 8 bits we're using here. Go back to that diagram. 8 bits. 3 address lines. 16 bits. How many address lines?
2 to the 6.
4. 32 bit 5. N bit memory. How many address lines? Look, exactly, yeah. So for n address lines, we have 2 to the n bits we can address. We've got a megabit to address. What is a megabit in number terms?
1 million. 2 to the 20.
2 to the 20. We have 2 to the 20 locations to address. How many bits in the address field?
20.
20! In this case, 8 bits, 2 to the 3, 3 address lines. 16 bits, 2 to the 4, 4 address lines. We will have 20 address lines. Let's draw some of them. One down to 20. But I don't want a single function of 20 variables. I want functions of 4 inputs. My little n, my interval size is 4. So partition that address field into n bits here and the rest. And this is going to be the n tuple And this now is going to be the function address. Okay, now you know how that works. How many functions can I put in that memory of 4 bits, and how do I organize it? How many functions? 20 address lines. I'm putting 4 of them to the entable size, because that's what I've given you. It leaves 16 for the function address. How many addresses on 16 bits are there? 16 address lines. How many numbers from 16 bits? 2 to the 16. 2 to the 16 is what? 32,000, isn't it? 2 to the 16. 65,000. 65,536. I can set up in that 1 megabit memory 65,536 different functions. Wow, that's quite impressive. Level 1 stuff.
So 2 to the 16 isn't 16.
Well, what is 2 to 16? 4 is 16. 32, 65,000. Work out the numbers yourself. It's going to be 2 to the 16. And this is going to be 2 to the 4. And how do I access those functions? The very first function, the inputs are on the entable line, A, B, C, D coming in there. Set the whole function address field to 0. It will only address one of 16 bits in the memory. And those 16 bits will depend upon the inputs of the function, A, B, C, D, and all the rest will be 0. For my second function, I can change the function address from 0,0,0,0,0,0 to 0,0,0,0,1. And that will address a different set of 16 bits. For my third function, I increment the function address, and there's another thing. So it's partitioning that memory into 65,536 different 16-bit groups, and they can be your functions. Now, if you have an access time of that memory of 1 microsecond, okay, to cover all functions, you've got to scan through all the function addresses and look at the output, so the output of the function. So you've got to do 65,536 accesses of that memory. And if it's working at a microsecond, it's going to be 65 milliseconds. Yep. Take the memory a little bit faster, and we're well within the time of the capture rate of an image, which is going to be milliseconds. So we can organize this system to scan between capturing pictures, can scan through the whole of the network. So we can actually implement these systems not as a parallel system, but as a serial system. So that's the concept of breaking up the memory. So let's now look at the schematic for the complete system. 1 page is needed for this. Here is your memory. Let's have the interval, which can go into a 4-bit buffer. That is a CPO. Remember CPOs? CISOs? PISOs, you must remember PISOs. Parallel in, serial out, shift registers. You direct entry to level 2, were you? That's a shift register that will convert the data into intervals. Serial data, parallel intervals. That has got to be fed from an image. Image buffer. And so that's going to take one output. Right. The image buffer has got to be addressed. That is effectively generating the mapping. It's selecting the first pixel of the first interval, the second pixel, and so on. If it were to be a linear mapping, where I was taking the first static mode, the first pixel, then the next, then the third, then the fourth, then the fifth, what would generate the function address, the access to that memory? I want pixel one by one. I want address 0, and address 1, and address 2, and address 3, and address 4. What's that? A counter! I daren't ask you what a counter is in logic. Cascaded asynchronous flip-flops. Never heard of it, no. Go on. Okay, so for a linear mapping, I can drive this with this addresses to the memory. A counter. If I want a random, this is a hard question, this is going to be. If I wanted a random sampling of the image, which is most probably what I would want, because it's more, we think nature is much more random. We have no knowledge of the content of images and we're trying to learn them. If I wanted a random set of numbers, just random, reproducible, no particular order, 5, 27, 61, 243, what circuit could I use for that? Any Germans here? We beat them, we won the war through this device. Yeah, what is that? Feedback shift
Register.
registers. So that could be a feedback shift register. Oh, you haven't forgotten those wonderful devices, generating millions of numbers from just giving a starting state of a buffer and a feedback function. And send them to Australia, and they can generate the same set of numbers. Fantastic. Right. If I wanted a particular optimized mapping, remember feedback shift registers will generate random or pseudo-random numbers. If I wanted a fixed number, I would need to store the numbers in the memory. Right. The function address. There's going to be 16 lines there. I want to produce a sequence of numbers there, starting from 0 and going up to maximum 32,000, whatever it is. What device do I need for there? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What's that? Counter. Right, so that's getting the information in. The memory, this is 1 megabit, needs a train test. And in terms of the memory, training is setting up the functions, testing is reading the functions. So there will be a read-write control on the memory. And the read is the test, and the write is the train. So when we're training the system, we are taking the intervals in. For each function defined by the function address, we will put a 1 in for the input occurring on the interval. For the testing, we are addressing the same function with the function address. We are taking the interval from the new data, and we are accessing the information at that location, and that comes out. The output is a single line because we're outputting the bits. It's a random access memory. and I want to sum the activity over all 2 to the 16 functions. I've got a single output, it's running, it's producing a stream of ones and noughts. I want to know the totality of ones and noughts in it. What do I put on the output there? Another counter, counting up the noughts and ones. And so this would be an asynchronous counter. Right. So we've got a system now which is a basic diagram of what could be a hardware system. And this would be for one discriminator. Most problems, well, quite a lot of problems, we have more than one class. Character recognition, you've got 26 classes. Face recognition, it can be a 2-class problem. It's you or it's not you. The one-many classification. But most of them have a number of classes. So if I wanted to recognize, say, this population of faces here, just you guys, I would need one of these discriminators for each of you. I'd throw an unknown picture to all of them, and then the one that matches gives us the highest response from the ones it knows. That input is associated with that class. So we might need more than one class. Now that is bit organized memory. If I take this structure and now make it byte organized, I could put other planes of memory in here. And if I put these on a bus, so all these lines go to all the different memories, then I can select on the memory the first bit, the most significant bit for class 1, the next bit for class 2, class 3, class 4. And I would need a counter on the outputs of each of those. So there is my counters behind. So the generating of the data, the interval sampling, and the addressing of the memory is common to every class. It's only when we have different classes we want to take the response to your detector, your detector, your detector, and give its individual response. We then have the responses coming out here, which are equivalent to the outputs of our net, and we then have rules for generating. And the simplest rule is you've got a series of responses, which is the highest response, associate the input with the one that's giving the highest response. So that is a brief sketch of a hardware structure. And that was a machine which was built at Brunel a long time ago, before you guys were born. But that was the basis of the Wizard pattern recognition system. I think one or two of you have seen it in the Science Museum. We've got it working about 1989. And it was a state of the art at the time. I showed you the picture of the Mark I perceptron at Princetown, which was 1950. A Wizard was about 1,000 times more powerful than that. But today, it would be trivial. You'd have it on your phone without even knowing it's there. So that is a hardware structure implementing the system. What if we go for really big systems? If we want large interval size, in nature we think neurons have thousands of inputs. If you followed my cost formulae, if n gets to the millions and little n gets to the thousands, that becomes an impossible amount of memory. You could easily put in system parameters that would use up all the known memory in the world. Like interval of 5,000 interval size and resolution of millions. So there comes a time when the hardware system runs out of steam that would take up all the memory that we have. Don't panic. We can revert back with modern technology to the original Browning and Bledsoe method, whereby you weren't using functions to store the intervals, you could store them on disk with fast access and modern technology. So that would be for large systems, but for systems you want to put on people's credit cards to recognize faces on SIM cards, that hardware method is quite plausible. It's cheap. I mean, the total cost of a 1 megabit memory these days, well, give them away free, don't they? If you work out your smart card the size of system that you could organize within that memory is pretty big. If you've got, there's 1 megabit, if you're talking about gigabits, hundreds of gigabits, or even a terabit, you can still get a pretty big hardware system. So, that's about my time run out, which is convenient because I want to leave neural networks now, and in 2 weeks' time, I will come on to the next part of the course, which is image processing. And now that's easier, because in image processing, we think we know what the functions are. In neural networks, we don't, we're trying to find functions. So the idea of image processing is normalizing, processing, and making it more reliable. Okay, so we'll start on image processing next week. If you want a seminar on any time, give me big notice. You're in the last term now. Don't forget the analog stuff. Keep thinking about it. Have a party tonight on Digital Next.
Thank you, sir.
Cheers.
Thank you.